Okay. Anyways, I think this looks good. Alright, so find occurrences of an element. I'm creating a vector of hints, and yeah, so this vector will contain the first occurrence, indexes of basically, like, so 0 is going to be the first occurrence, the index of the first occurrence, the index of the second occurrence, index of the third occurrence, index of the fourth occurrence, and we will use that to I don't know. Okay, yeah, we can figure out the edge cases, but right now, what do we add to frequencies? We just add I, right? Yeah. And then after we're done with this, let's create another one of these. So for now, we can go. And then for every query in queries, what do? We see if there is a first occurrence. So if Q less than equal to queries.size, res.push back. The index, right? So frequency of n-1. Yep. As -1. I think it should be this simple. Oh man. What is this, man? Res.push underscore back frequencies of Q-1. Where is the fire as always? Yeah, it's a little bit about there. Now this should work. It's not that good of a runtime, but that should be it, right? Couldn't be like what? 43 ms C++. Let's see. Yep, I wrote the optimal solution. This should be an easy. Should be an easy. Whatever. Yep. Okay. It's pretty easy. Create a vector that contains. Okay. Let me get back. This looks good. It's actually the optimal solution too, so that's good. What do we have up next? Either this or that. I don't really get it. Okay. Okay. What was the next problem? Excuse me. Anay, anay. Oh. Okay, no distinct colors on the walls. It's so simple. No? Isn't this too simple? Oh, we don't have to return the number. Um, okay, why is this wrong? Why am I getting 3, 4, 5? How many? What is it asking me? It's asking me the number of colors after the ith query. Oh, I didn't even look at the problem, right? Okay, number of colors after the ith query. So this is completely wrong. We can't have this. But I think this might be useful. Let's see. If queries is this 14251334. Okay, that's our colors query. Limit is 4, so we have 5 balls. So that's 0, 1, 2, 3, 4, 5. Okay, I mean, no, not 5. It's 0, 1, 2, 3, 4. Okay, and then ball 1 is colored with 4. That means there are one distinct color after this query. Okay, and well, how do we get that? There's one distinct color after this query, and when ball 2 is colored with 5, there are two distinct colors. So after every query, we can go through the whole list, right? Okay, yeah. So for each query, we're just going through the list and counting the distinct number of yeah, 3. When we replace this with 3, then we get 2. So there's 1, 2, 2, and then 3. So the answer should be 1, 2, 2, 3. Yeah. And how do we do this? So what is a hint that we could have? 2 hash maps to maintain the color of each ball and the set of balls with each color. Color of each ball. Okay, hash maps with the color and then set of vals with each color. Okay, so ball, color, and then color set of vals. Okay. What does that help us with? So let's say we have ball to color, right? We do have ball to color. Okay. And that is going to be just this array that we build, right? That is ball to color. That is just this. Okay. And then it's color to set. So let's say 4 has like 2 and 3. 5 has 4. What does that help us with? Oh, we can use the length of this at every single iteration. क्या कह रहे हो? क्या कह रहे हो? हाँ. Every single iteration. क्या कह रहे हो? क्या कह रहे हो? हाँ. Okay, we go back. Okay, क्या सोच रहा हूँ यार मैं. Anyways, so yeah, this das ist gut. Das ist gut. So whichever color here does not have an empty set. Right? Whichever color does not have an empty set, you can just return the number of colors. Yeah, I think that's kind of the thing that we're going for. Okay, so we do have the balls. And now what we do is I'm just gonna go back to color to IDX. Okay. Okay. And then balls of Q of 0. Yeah. Okay, and now I think the magic is in this loop. So we do set balls of Q0 to Q1, and we also set color to IDX of Q1 if color to IDX that contains if it doesn't contain that, then Then we set it to insert into the set. What do we want to insert in the set? We want to insert. What do you want to insert to the set? Set dot insert. If it does contain it, then okay. And then now that this is okay, I think we can just iterate over this should be the right answer. Why is this failing? So why is this 1, 2, 3, 3? Alright, now we have to start our debugging. Put our debugging hat on. What does this even mean? So where is my timer? I am almost, oh no, I'm 1 hour in. How many problems am I in? 2 problems in? Oh my god, bro. 2 problems for 1 hour is terrible. I need to do way better. I'm just gonna ask it to debug this. Memory limit exceeded. But I think I'll be able to get this if it wasn't for whatever. Int to int instead of int to set. Auntie?
अभी भी वही कुकिंग ऑयल? Here are 3 reasons why you should use Saffola cold press oil. No heat or chemicals. इसमें है zero trans fat. चाहे frying हो या sorting या फिर एक simple तड़का, this oil is suitable for all. Backed by 50 years of heart health legacy, so I can trust it without any doubts on quality or purity. So are you convinced or not?
Stop before you buy this. This exact product could be cheaper.
好，各位好，我们来看今天leetcode的问题。好，今天的问题是第3160题，所谓的 Find the number of distinct colors among the pools。基本上它就是要找出在一堆球上面不同颜色的一个数。啊，它是一个中等难度的题目，所以它这边的题目大概是这样，就是说，它会给一个整数叫 limit， 然后一个2D 的一个阵列叫做curve， 然后接下来我们就用一个单一的一个回圈做一次走访大概答案就可以出来。那所以我们在每次的 query Q0 当然就设为 X，Q1 就设为 C X 代表让球的编号 ，C 代表的是这一次你要着上的颜色的一个编号。那如果说 MP
Hello guys and welcome back to Leet Logics. This is the count number of nice subarrays problem from LeetCode and the number for this is 1248. So in the given problem we have an integer nums, array of integer nums and an integer k. We are given with the fact that a continuous subarray is called nice if there are k odd elements in it. So if a continuous subarray contains k odd elements, it is a nice subarray, and we have to return the number of nice subarrays present in the array nums. So let's see what are nice subarrays through an example. So suppose we have example 1, nums equal to 1 1 2 1 1 and k equal to 3. So we have to take continuous subarrays with exactly 3 odd numbers here. So if you carefully see, you can find this subarray 1 1 2 1 and another subarray 1 2 1 1. The process. So first of all, we have to initialize some variables. We will initialize a count variable that will be an array to store the prefix sums, and we'll set count of 0 to 1 because initially when we before starting the iteration there are no odd elements in the array. We assume there are no odd elements in the array, so that's why count when there are no odd elements, 0 odd elements is set to 1, and we have a variable answers to store the result and t to store the current number of odd numbers while iterating through the array. Then in the next step we have to iterate for in the each element of the nums, update the count of t, and for this we'll use a bitwise operation. We'll do a AND with 1, and we'll check if there exists a prefix sum t minus k, and if there exists we'll add it to the count to the answer and update the count of the prefix sum t in the count. We are doing this because if we encounter a variable, we can find the number of remaining odd numbers that we require from t minus k and we'll get the answer. So for this example, nums equal to 1 1 2 1 1 and k equal to 3, we have a tabular or visualization. So when we are at index 1, nums of I is 1, odd count is 1 because this is odd. The count updated becomes 1 and 1 because 0 was already 1 before iteration, and because due to this also becomes 1. And when we do k minus t, this part k minus t, this gives negative because t currently is 1 and k is 3, so k minus t is minus 2, so we don't have to do any operation here, we can skip to the next. Then when the index becomes 1, we see nums of I is 1, so the odd count becomes 2 and the count will be updated, so the count of 2 becomes 1 and last bit set to 1. So we have used that factor to check if it is odd or even.
Hello friends, today I will solve a LeetCode daily challenge called count number of nice subarrays. So the problem is, given an array of integer nums and an integer k, a continuous subarray is called nice if there are k odd numbers on it. So at index I will consider all the subarrays ending at index I. Then out of all those subarrays that are ending at index I will only consider the nice subarrays. So let's understand this approach from the given pseudocode. First, I am declaring two variables, n that stores the length of nums array and result. Then I am running a for loop from index 0 to index n minus 1. So here I am calling the method count nice subarrays. So it counts all the subarrays which are nice and ending at index I. Then at the end I'm returning the result. So let's look at the method count nice sub-arrays. So here I am declaring two variables, count equal to 0 and result equal to 0. So while I is greater than 0 and count is less than equal to k, if the nums of I is odd, I am incrementing the count, that is count of odd numbers. And if count is equal to k, I'll increment the result. At the end, I'll return the result. So this method loops from index I towards index 0. So you can say it is upper bounded by big O of n. So the time complexity will be, we are running a for loop from index 0 to n minus 1, and within the for loop we are calling a method which is upper bounded by big O of n. So the time will be big O of n square. So if you implement this approach, it will result in TLE. So this is not optimal. So let's look at another approach which runs in linear time. So let's discuss approach 3. So the idea is, if the subarray from index 0 to I contains x odd numbers, and the subarray from index 0 to j contains y odd numbers. So the subarray from index I plus 1 till j contains y minus x odd numbers. So if y minus x equal to k, then subarray from I plus 1 to j is nice. So let's understand this pseudocode. So first I am declaring two variables, result equal to 0 and odd count equal to 0. Similarly, I am declaring a hash map and I am inserting key 0 with value 1 to the hash map. This is required to count the subarray having k odd number of elements and starting from index 0. So we will discuss why this is required when I will dry run for this example. Then for each number in nums array, if the number is odd, I will increment the odd count. So using the idea I discussed in the right, we can say if the hash map contains the key odd count minus k, I'll add its value, that is hashmap.get, to the result. That is, these many number of subarrays will contain exactly k odd elements. And at the end, I'll update the hash map. That is, I'll increment the value for this key odd count. So here, for this key odd count, I'm incrementing its value by 1. Then at the end, I'll return the result. So let's understand this approach with the given example. So I'll start with the first number. So before I'll declare the variables result equal to 0, odd count equal to 0, and a map which contains the pair 0 1. So for the first number, that is num equal to 1, I can see the number is, and I'll return the result. So let's understand this approach with the given example. To the result, that is, these many number of subarrays will contain exactly k odd elements. And at the end, I'll update the hash map. That is, I'll increment the value for this key odd count. So here, for this key odd count, I'm incrementing its value by 1. Then at the end, I'll return the result. So let's understand this approach with the given example. So I'll start with the first number. So before I'll declare the variables result equal to 0, odd count equal to 0, and a map which contains the pair 0, 1. So for the first number, that is num equal to 1, I can see the number is odd, so I will increment the odd count by 1. Then I'll check if the hash map contains the key odd count, that is 1 minus 3, that is minus 2. So I can see the hash map doesn't contain the key minus 2, so I'll ignore this if condition. Then I'll add the odd count, that is 1 to the hash map. So I'll insert a pair 1 comma 1 to the hash map. Now I'll go to next element, that is num equal to 1. So here I can see this is odd, so I'll increment the odd count by 1. So I have declared two variables called result and odd count. That is, if nums of end is odd, then current odd count will be incremented by 1 because I am doing mod by 2. And if the number is 7, the mod will be 0, the current odd count remains same. So if the current odd count is greater than the maximum odd count that is allowed, so it means we have reached the limit of right window. So now we need to shrink the left window. So that is, while the current odd count is greater than the maximum odd count, I'll
Hi, Jimmy Pays here with Bitrix 24, a free CRM that will help you achieve explosive growth.
So let's continue with our greedy algorithms playlist. But before that, hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So the problem that we will be solving today is jump game. So you'll be given an array which will have integers. And the problem is stating you'll be standing at the first element. And every element tells you how much maximum you can jump. For an example, if there is 2 over here, it means you can jump to this place or you can jump to this place, not beyond it, not beyond 2 places. If there is 3, you can jump here, you can jump here, you can jump here. And the problem is asking you, if you're starting at the first element, can you reach the last element by jumping? Let's try it out. Over here, we have 2, right? Which means I can take a jump of 2. A maximum jump of 2. So if I go here, there is a jump of 1. So I'll go here and I cannot jump further, which means I cannot. But the question is stating maximum that you can take. I'll not jump the maximum. Instead, I'll jump by 1 place. And from here, I'll jump 3 places. So eventually, I can reach the end. Hence, true, possible. Okay, let's try out the other example. I'm standing over here. Okay. Can I reach the end? From 2, I can either reach here, I can either reach here. From not able to cross 0. I am not able to cross 0. Forget about the last. I cannot cross turning across. Go here, right? It's important that you can cross the 0, right? So this is what you'll have to do. Given an array, you have to tell me if you can reach the end or not. How do I solve this problem? Let's take this example. I can either go to this one, okay, add all possible combos. You can try out all possible combos. You cannot cross 0. Thereby, it is not possible. Okay, now let's try out. From here, I can go here. From 2, I can go here or I can go here. From 4, I can go here, here, here and here as well. I don't need for every possible. It's going to be x whenever you reach and complete mine. No one would have reached there. This place. So over here we have one place we can jump. So the max we can go is till 1, not beyond it. Perfect. Next we come to this index. We come to this index, and to ease out understanding, I'll write down the index numbers. From here, where can I go? 2 places more to the index. Perfect. And I can still reach 6. 5 plus this, that means so I'll just 1. Reaches 3. Perfect. Next, I can go to the rest 2 plus 1 means 5 stacks. Max is 9. Next, let's see how I can solve this until now. What we will do is we'll say, okay, what is the max index till which we have gone till now? Initially at 0, so we haven't gone anywhere. Okay, perfect. So we are standing at here, and we are at this place. So over here we have one place we can jump. So the max we can go is till 1, not beyond it. Perfect. Next we come to this index. We come to this index, and to ease out understanding, I'll write down the index numbers. Perfect. So we are at 2. From here, where can I go? 2 places more. 2 places more. I'm standing at 1. I can go to 2 places more, which makes it to the index 3. To the index, I can go to 4. 4 means I'm standing at the second index. 2 plus 4 is 6. I can go a max of 6. I can go a max of 6. Perfect. Next, standing at 3, I can go a 1, which is 4. No need to update max because I can still reach 6. I can still reach 6. Perfect. Next, I can go to this one, which is a 1. I don't care. I can still reach 6 plus 2 is 8. You can stop over there because you have definitely reached. Okay. So we stand over here. My bad. Yeah, we stand over here. How this works. 0 standing at 1. Okay. So the max that I can reach is the index 0 plus 1. Over 2. So the max I can reach is 1 plus. I can go to the next, which is 3. So I can go from 2 plus 3, which one is 4, 1, 5, 5 plus 0 is 5. I don't care. Next I reach 6. And this is where I say, hey, wait. The max you were able to reach was 5. How did you come here? As a person, you cannot arrive here. You cannot. Understood. Return false, return false. Simple, right?
My wife called me lazy because I never do the things I say I'll do. I thought it was depression. We were both wrong. The kitchen light has been out all week. My wife asked me to change it on day 1. She reminded me on day 4.
Right, yeah.
She stopped reminding and changed it herself on day 7. I was home the entire time. She told her sister I was lazy. I heard it through the wall and I didn't argue because I thought...
I'll be
There though.
on the function. So you're typically given the array, correct? You can figure out the size of the array by array.size.
Oh, this feels so easy now. Hold on, I think I can do this pretty nicely. Jump game. Okay.
Rain probability 20%.
subtract.
Where do I start? Can I say max index can always be updated to max of max index comma I plus array of whatever jump is given to you? I can. And if at any moment, or maybe you can just skip it. You can write if max index at any moment is greater than equal to n minus 1, you can stop. And if this condition, remember, if this condition never happens, which means you're able to reach the last index, thereby you can straight away say return false. Return true. To optimize, you can definitely insert a if condition. In case during the journey you are able to reach, you can put an if condition over here. That will be it. What is the time complexity? Bgo of n. What is the space complexity? Bgo of 1. That's it. This is the most optimal solution. Again, I was greedy. I tried to jump the maximum and see if I'm able to reach the end or not. Simple sorted greedy algorithm. The catch over here is 0. If you're able to cross 0, you will be able to reach. And if there are no zeros,
God damn, this is so greedy.
so let's continue with our greedy algorithms playlist. But before that, hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So the problem that we will be solving today is Jump Game Part 2. In case you haven't seen my Part 1 video, please go back and watch it. So what is the Part 2 stating? It's stating that you will be standing at the first element. You're given an array. Every element tells you what is the maximum jump that you can take. For an example, if it is given as 2, you can jump till here, either of them. This is the maximum that you can take. So you can jump to either of these elements. Now the question is, tell me the minimum number of jumps that it will take to reach from the start till the end. From the start till the end. And it is guaranteed that you will reach the end. It is guaranteed. The test cases are given in such a way that you will definitely reach the end. In the part 1, the question was, will you reach the end? Over here, the question is, tell me the minimum jumps that you will take to reach the end. Got it? So what will be the answer for this particular test case? What I can do is from here, I can jump till here, which is a jump, single jump. From 1, I can take one more jump, which is another jump.
Ooh, minimum jumps.
So I'm taking 3 jumps.
I knew he was going to ask me that.
And
so
this
hard.
is going to be the answer. Minimum jumps. You can try out all of the possible ways. And 3 is the minimum answer that you will get. Now, if this problem comes up in an interview, what is the extreme naive solution that you can think of? I know one thing. Starting at the 0th index. And there are 2 possible ways. One is this. One is this. From here, there are 3 possible ways. So every index has different ways. Can I try out all ways? Yes, I can try out all ways. And then can I pick the minimum of all of them? I can, right? So what I will do is I'll just take a smaller example. Let's take a smaller example, which is, if I take, that will be 2 jumps. If I take 2 jumps, I'll reach 3. That will be 2 jumps. If I take 3, I'll be reaching the 4th index, and that will be 2 jumps. And if you carefully see, this is one of the ways. This is one of the ways. This is one of the ways. And this is going to tell you, hey, you've reached your end. So you're going to take minimum of this, and minimum of this. So eventually, it will be returning you 2 because you've taken 2 jumps. So you'll get your answer as 2 for this particular test case. You're going to try out all possible ways. Plain recursion. Very simple recursion. Can I super quickly write down the recursive code? Maybe yes. So I'll be right. Okay. Function. Maybe I can take an index. I can take the jumps. and this will be called with f of 0, 0 with the array, obviously. You know what is the base case? What is the end case? I know one thing for sure. The end case is, hey, if at any moment the index is greater than n minus 1, that means we either reached or crossed over. And if that is the case, I'll be like, hey, can you return? Now this is very important. Can you return? What will I return? I'll be returning the number of jumps, right? Perfect. Done. What is the next thing? I'll be like, okay, how many jumps can I take? I can start from 1. I know for sure I can start from 1. And I can go ahead till array of indexes. Those many jumps I can take. I'll have to take the minimum of all of them. So maybe I can keep a mini equal to something as, I need a mini answer, right? So I'll keep it as int max. Perfect. And what I'll do is mini equal to minimum of mini, right? Comma, what I can write is function of standing at index. If I take the jump I, I'll reach index plus I, and the jumps will be added by plus 1. Perfect. So I'll take all the jumps, and whatever is the minimum, I will straight away return it. Done and dusted. That's it. Just make sure you don't start with 0. Then it will go to the same index. There's no point in jumping to the same index. So this will be the recursive code. And if I have to write down the time complexity, this will be exponential in nature. You are going for n indexes. So n to the power n, assuming all the jumps are till n or somewhere near about that. So it can go exponential in nature. What about the space complexity? I'll be using auxiliary stack space of Pico of n. Correct. Now, what you can do is, this is exponential. You can optimize this. Yes, you can optimize this. How can you optimize this? Again, if you haven't seen the dynamic programming playlist, don't watch this dynamic programming portion. If you know dynamic programming, you can watch it. So for the people who have seen my dynamic programming, you know how to optimize an exponential state to a quadratic state. You know it. There are two variables that are changing. One is index, the other one is jumps. So what you can do is, instead of returning mini, you can technically declare a dp of n, correct? And you can say dp of index and jumps equal to mini. And over here, you can say, hey, if, not here, over here you can say, hey, if dp of this state has been visited previously, make sure initially you have -1, has been visited previously, you can return dp of index jumps. Quite simple. So if you do this, the solution will be converted into a ego of n square solution.
What they really sold was a promise to make you rich and successful. I am not going to make you rich. I can't promise you that. Nor can I promise that you will even enjoy your riches. But what I can promise, Andrew Tate, Ty Lopez, Jake Paul, all made millions selling their houses. What they really sold was a promise to make you rich and successful. I am not going to make you rich. I can't promise you. Nor can I promise that you will even enjoy it. But what I can promise.
Put the bag down, sir. I can take these to your room for you.
Oh, thank you.
Cash tip is customary.
Oh, I don't think cash don't expect it.
That's okay. I accept that.
Oh, we don't have that either.
Okay, I also accept cash app.
Yeah, we can put that on content later.
organic rutabaga giblets, sir. You're going to transform those 50s into ones. At which point you will come back here and tip me for my exceptional service, sir.
And the alternative is I just take my bag up myself.
Correct, sir.
Yeah, I might just do that.
Okay, first put the bags down, sir. I can take these to your room for
ये क्यों
जा रहा हूँ
पढ़ना था ना आपने? फिर बीच में फोन क्यों खुल जाता है?
जा रहा हूँ
First put the bags down, sir. I can take these to your room for you.
Oh, thank you.
Cash tip is customary.
Oh, I don't have any cash, sorry, I just got it here.
That's okay, I accept Venmo.
Oh, you don't have any.
Okay, I also accept Cash App.
Yeah, we don't have any.
Perfect, so what I'm going to get you to do is go ahead. Organic rutabaga giblets, sir. You're going to transform those 50s into ones. At which point you will come back here and tip me for my exceptional service, sir.
And the alternative is I just take my bag up myself.
Correct, sir.
Yeah, I might just do that.
Okay, first put the bags down, sir. I can take these to your room for you.
Oh, thank you. Nothing in the sauce, where you coming from?
Came all the way from Toronto, Canada, 6. But I also live in Brenham, Texas. So Brenham.
Same thing.
Yeah,
Same thing. Thank you.
Love. I gotta try something. Loaded fries. I came to you, by the way. Fire. Fire, Hawaiian bun, great.
Same thing. Thank you.
Trap down.
Nothing in the sauce, where you coming from?
Came all the way from Toronto,
ले
Canada.
वैसा फोम वोम है इसमें पूरा भरा हुआ नहीं है इतना
हम कोई बात नहीं और ले आऊंगी
Jesus Christ, Andrea, it's so shaking. I ain't got no.
किलो तोड़ ले आऊं कितने प्रॉब्लम्स हो गई आगे आज की
अबाउट 4
10 करनी है ना
कर रहा हूँ हाँ होने वाली है
Message to all the tech bros out there. My name is Jay. I'm the founder of Meme. And I'm going to make you lazier than you've ever been by giving you access to this device.
बेटा पीना मैं और ले आऊंगी
Taking my pen.
Oh shit. What am I doing? Man. What am I doing, man? Look at me.
To a BGO of n square solution with a space complexity of BGO of n square. Now this is what it will be converted into. Okay, perfect. I think we have pretty much understood. We have understood it, right? What is the next thing? Again, you can optimize this. You can optimize the space, go into space optimization. I'll leave that. This is not a DP problem. So I'll leave that. In case you have seen my DP playlist, you know how to solve it. Obviously, the interviewer will not be happy with the big of n square, and he'll ask you to optimize it. So I'm looking forward to optimize n square. That means I'll have to go somewhere around big of n, correct? Okay, how should I think a big of n solution? That's a big question, right? What was I doing in the recursion? I was trying out all possible ways. Then I took the minimum. Can I try out all possible ways? Maybe I can. I know at zero's jump, I'm standing at the first element, right? If I take this jump of 2, what are the possibilities I can go to? I can go to here, I can go to here. That means I can take a jump of 1, and I can reach either 3 or either 1, right? Okay. So I'll keep it in mind that this portion can be reached. Remember this? Now I'm dealing with ranges. Instead of doing the recursion for this, I'm carrying the range. I'm saying jump 1 means this much. This one can be reached in jump 1. Already done a similar problem, which is valid parenthesis string. Go back and watch it. We optimize the recursion in 2 ways. Okay, so I'm saying instead of recursion, I can reach from here to here. If I take a jump from here, I can either reach here, which is going to take me like 2 jumps. There's no point because I can reach this place in 1 jump. So I'll not do this because recursion means minimum. I'll do the minimum. Okay. Thereby I can reach here or I can reach here. So I can reach both the places. So that means the farthest I can reach is this. Okay. For this, the farthest I can reach is here. Thereby, I'll be like, this is the next range I can reach by taking 2 jumps. In range concept, I tried jumping from here and the max I will go. You can go here, which is S in this 2. So I know I can reach till the last. I can reach till the last. Okay. For this one, I can reach here. So I know the max I can reach is here. So from here to here, I can reach in third jump. That is going to be the last range. Once you reach the last, you stop. And what is the last range reachable at? It's reachable at 3 jumps. It's reachable at 3 jumps. What I did was, I didn't create individual recursive calls. I carried a range for it. Instead, I carried a range. Let's check out the code. It's going to be super easy. I'll write a very, very simple code. Don't worry.
Name one thing in your life that wasn't built by someone. Your home, your office, the road you drove.
You tell me the initial jumps. You know it, right? Initial jumps is 0. Tell me the initial range. This much. So maybe you can carry a L and a R, which is initially at the 0th index. Okay. From here, where can I jump? Till here, till here. What is the next range? The next range is this. So where will L go? Where will L go? Please focus. L will go to one place ahead of R. One place ahead of R. Where will R go? To the farthest that I can jump. Perfect. And with this jump, what will be the value of jumps? 1. So if I take 1 jump, I will reach this range. Done and dusted. What is the next one? For this 3, the farthest I can go is this much. For this one, the farthest I can go is this much. So from this range, the farthest I can go is till here. So what I'll do is, I'll update L and R. Again, focus. L will go one place ahead of R. R will go to the farthest. Done. What will happen to the range? What will happen to the jumps rather? 2. Okay. Standing at this place. Again, 4 can go how much? Can go here, 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 here. Farthest. Okay. 1 can go here. The farthest you can go from this ranges till this place. So what you'll do is, first update L, which is going to be 1 plus of R. Then update R, which is going to be this. And the moment R reaches or crosses n minus 1th index, by the way, update the jump for this one. Once it crosses the n minus 1th index, the jumps is going to be your answer. Got it? Very simple. The code is going to be super duper simple. I'm going to write the function. I have the array. Maybe you're given the size of the array as well. Or if not, you can compute the size of the array. What do I need? Okay, initially, I am doing 0 jobs. Having L initially at 0, R initially at 0. I'm going to try out everything now. Okay, I can try out till my range. I know the right of range should be lesser than n minus 1. If it exceeds, goes at n minus 1 or beyond n minus 1, I stop. Okay. At this time, what do I do? For this range, I find out what is the farthest I can go. What is the farthest? Okay. So I'm like, what is the farthest, right? Maybe I can call it farthest equal to 0 because I'm trying to get the farthest. Now what I can do is, I can start from index. What is my range? It's from L to R, right? It's from L to R. So what I will do is, I'll start traversing from L to R. Okay. And I know one thing, if I'm standing at I can go till the jump allowed, and I need to see what's the farthest I can go. So I'll be like, okay, what's the farthest? It's going to be max of this one, comma, farthest. Pretty simple. Once this is done, once you've traversed for all elements in that range, you know the new range. And what is going to be the new range? L is going to be at R plus 1, right after that element. And R will be the farthest. And please make sure you update jumps. So at the same time, you can do jumps equal to jumps plus 1. And you can end the while loop. And once you have ended the while loop, what you can do is, you can straight away return the number of jumps it ended up taking. And that's it. That's pretty much it. Done and dusted. Now, what is the time complexity? On a very naked eye, it might look like while loop into a for loop, ego of n square. No. What did you do? First you traversed 2, then you traversed 3, 1, then you traversed 4, 1, and eventually you reached. So what you are doing at the end of the day is traversing each element one by one. This while loop is just to check, did you reach? So eventually, the time complexity is big O of n, which is linear in nature, and the space complexity is big O of 1. That's it. That is it. So let's see. I thought of a recursive solution, and instead of doing the recursive tree, we kept a range. Converted the recursive solution into a range-based solution, right? And this is how you can do it. Why is it under greedy algorithms? The reason being, I'm trying to reach the farthest. That is why this is under the greedy algorithm playlist. I hope you have understood. How I started with a recursion solution, then how I optimized that recursion solution into a linear solution. So this will be it for this one. So if you're still now watching and if you've understood everything, please do consider giving us a like, and if you're new to our channel, do consider subscribing to us as well. With this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye-bye. Take care.
Whenever your heart is broken, don't ever forget you're golden.
Do you perchance have a proclivity for pickled, no bacon, animal-style nipples? What? My apologies.
If you are following the AI evolution, you already know that agentic AI workflows are everywhere. This is the shift where AI stops responding and actually starts taking actions. And if you're looking to level up your
I am trying to ascertain if that individual is yourself.
Oh no, I got chips, so
Then you traverse 3.
Okay. Well, although I am disappointed in the outcome of this interaction,
So if someone is asking you,
I have thoroughly enjoyed this interaction with you, and thank you for taking the time out of your busy schedule. Now, if you could do so, please a Google review, and there is an option to leave a small token of your appreciation and gratitude. 50 to 20% is customary in an exchange such as this. God bless you, and God bless you.
I can see कि पढ़ाई नहीं हो रही है.
क्या यार ये स्कूल
गर्मी लग रही है बेटे. छोड़ दो.
जा रहा हूँ
6 घंटे मुझे आपसे फोन लेना है.
6 घंटे मैंने रख दिया.
what is the minimum jumps taken till 4? Like 2 jumps. Straight away now. Okay. From 4, where can you go? You can go with the range, check out the code. It's going to be super this much. So maybe you can carry a L and a R, which is initially at the 0th index. Okay, from here, where can I jump? Till here, till here. What is the next range? Range. It'll be like the next range is this. So where will L go? Where will L go? Please focus. L will go to one place ahead of R. One place ahead of R. Where will R go? To the farthest that I can jump. Perfect. And with this jump, what will be the value of jumps? 1. So if I take one jump, I will reach this range. Done and dusted. What is the next one? For this 3, the farthest I can go is this much. For this one, the farthest I can go is this much. So from this range, the farthest I can go is till here. So what I'll do is, I'll update L and R. Again, focus. L will go one place ahead of R. R will go to the farthest. Done. What will happen to the range? What will happen to the jumps rather? 2. Okay. Standing at this place. Here. Farthest. Okay. 1 can go here. The farthest you can go from this ranges till this place. So what you'll do is, first update L, which is going to be 1 plus of R. Then update R, which is going to be this. And the moment R reaches or crosses n minus 1th index, the jumps is going to be your super duper. So maybe you're given the size of the array as well. Or if not, you can compute the size of the array. What do I need? Okay, initially, I am doing 0 jumps. I'm having L initially at 0, R initially at 0. So I'm going to try out everything now. Okay, I can try out till my range. I know the right of range should be lesser than n minus 1. If it exceeds, goes at n minus 1 or beyond n minus 1, I stop. Okay. At this time, what do I do? For this range, I find out what is the farthest I can go. What is the farthest? Okay. So I'm like, what is the farthest, right? Maybe I can call it farthest equal to 0 because I'm trying to get the farthest. Now what I can do is, I can start from index. What is my range? It's from L to R, right? It's from L to R. So what I will do is, I'll start traversing from L to R. Okay. And I know one thing, if I'm standing at I can go till the jump allowed, and I need to see what's the farthest I can go. So I'll be like, okay, what's the farthest? It's going to be max of this one, comma, farthest. Very simple. Once this is done, once you've traversed for all elements in that range, you know the new range. And what is going to be the new range? L is going to be at R plus 1, right after that element. And R will be the farthest. And please make sure you update jumps. So at the same time, you can do jumps equal to jumps plus 1. And you can end the while loop. And once you have ended the while loop, what you can do is, you can straight away return the number of jumps it ended up taking. And that's it. That's pretty much it. Done and dusted. Now, what is the time complexity? On a very naked eye, it might look like while loop into a for loop, ego of n square. No. What did you do? First you traversed 2. Then you traversed 3, 1. Then you traversed 4, 1, and eventually you reached. So what you are doing at the end of the day is traversing each element one by one. This while loop is just to check, did you reach? So eventually, the time complexity is big O of n, which is linear in nature, and the space complexity is big O of 1. That's it. That is it. So let's see. Thought of a recursive solution, and instead of doing the recursive tree, it kept a range, converted the recursive solution into a range-based solution, right? And this is how you can do it. Why is it under greedy algorithms? The reason being, I'm trying to reach the farthest. That is why this is under the greedy algorithm playlist. I hope you have understood. how I started with a recursion solution, then how I optimize that recursion solution into a linear solution. So this will wait for this one. So if you're still now watching and if you've understood everything, please do consider giving us a like, and if you're new to our channel, do consider subscribing to us as well. With this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye, take care.
Whenever your heart is broken, don't ever forget you're golden.
और दशहरी सो 120
友達と一緒に昼ご飯も食べます。いいですね。Before, in our lessons, we mostly speak in Catalan. Now, I feel like 70% of our lessons are in Japanese. So if I hear something in an anime or a movie, I ask Maria and she builds the...
So with this video, we will be starting off with the greedy algorithms playlist. As usual, it will be a continuation of the Strivers A to Z DSA course. And in case you haven't checked it out yet, there is a link in the description. Make sure you check it out. But we're starting off, hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So the problem that we will be solving today is assign cookies. So what is the problem statement? Problem statement is, there is a parent, right? He has n children. Every children has a greed factor. The first children has a greed factor of 1. The last children has a greed factor of 4. So every children has a greed factor. Along with this, the parent also has m cookies. The parent also has m cookies. Every cookie size is known to the parent. The first cookie has a size of 4, whereas the last cookie has a size of 3. Now, what is the definition of greed? Let's take the third children. The third children has a greed factor of 3. So he'll only be satisfied if you give him a cookie which has a size greater than equal to 3, which means you can give this one, you can give this one. You can only give this particular cookie or this particular cookie. Nothing apart from this. So you can satisfy this children by giving one of the both cookies, right? Now there is a twist. You can pick up one cookie and you can give it to only one children. You can pick up one cookie and you can give it to only one children. Now your task is to make sure that you can assign maximum number of cookies to the children's. Right? The more children's should get the cookies. Let's try out. If I have a greed factor of 1, can I give this particular cookie? Maybe yes. So I'll give 4 to it. So this is gone. Okay. If I have a greed factor of 5, can I give it a cookie? I cannot, because I don't have anything that's greater than equal to 5. So I cannot. So I cannot satisfy this particular children. Okay. Can I satisfy this one? Yes. The 4 is gone, but I still have a 3. I still have a 3. So I'll give 3 and this is also gone. Can I satisfy this children? I cannot, because I don't have anything else. And I cannot reuse 3. I cannot reuse 4. I don't have anything. So I cannot. Can I satisfy 4? I cannot. So overall, I was able to satisfy 2 children's. But the question is that you have to maximize the number of children's. So maybe I can try some other pattern. Let's try out some other pattern. Okay. What if for this, I'll give this particular one, or maybe this particular one, doesn't matter. Okay, I'll give 1, that's done. For this 5, again, that's not possible, so that's off. For the 3, I can take up 3. Okay. For the next 3, I can take up 4. Okay. For the next 4, I don't have anything. So if I follow this particular distribution, I'll be able to satisfy 3 children. And this is the maximum you can do. You can try out different scenarios, but this is the maximum that you can do. You don't have to return which children you are able to satisfy. You just have to return the number of children you were able to satisfy. So did you see a pattern? What did I do? If it was 1, I need someone who is greater than equal to 1. So I tried assigning the smallest values, the nearest values to 1, the nearest values to 1, not 4, not 3, not 2. I was acting greedily. I don't want to spend a lot. Let's assign this 1. Let's keep the bigger values for someone who has a better greed factor, right? Better greed factor. And this is greedy. You're being greedy. You're being greedy because you only want someone greater than equal to 1. You don't give him a lot. You say, you're satisfied by 1, keep 1. Why take 4? You're being greedy. And this is what greedy algorithm is. So what I will do is, I'll take the size array and I'll sort it because I need the smallest number of cookies, like the smaller numbers. And that will be 1, 1, 2, 2, 3. So what I've done is, I sorted down the cookies, okay? After that, what I'll do is, I'll take the greed factor and I'll sort it as well, which is 1, 3, 3, 4, and a 5. So I've sorted this as well. Perfect. Now what I will do is, I'll take 2 pointers. So maybe you can call it as the left pointer and you can call it as the right pointer. Now what I'm saying is, hey, listen, I have a cookie which has a size of 1. Can I assign this to this one? Yes, I can. So if I can assign this, I've satisfied 1 children. I've satisfied 1 children. So I'll move to the next. I'll move to the next. Once I move to the next, I know one thing. This is done. This cookie has been assigned. So I'll move to the next. And now I'm asking, can I assign this one to any one? So I am at 3. I cannot. And if I cannot assign it to 3, I'll not be able to assign it to anyone beyond 3 because this is a sorted array. I'll not be able to assign it anyone to the right of 3 as well. So not possible. This cookie cannot be assigned. Okay, I'll try the next one. Can 2 be assigned? No, it cannot be. So I'll try the next one. Can this 2 be assigned? No, it cannot be. So I'll try the next one. Can this 3 be assigned? Yes, it can be assigned because this 3 can be assigned to this one. So you'll assign this to this particular children. This children is satisfied. Hence, we'll move to the next children. So what I can say is this particular cookie has been assigned. Let's move to the next one. Can I assign this cookie to this one? Yes, because this particular children has a grade factor of 3. So I can. And if I can, this children is also satisfied. So I'll move to the next children. And at the same time, I know this cookie has been assigned. So the left pointer crosses the cookies array. I don't have any further cookies left. So what you can see is, if I have to write down the indexing, 0, 1, 2, 3. You're able to satisfy 3 children. And that is why you're standing at this one, because this was not satisfied. You're standing at a third index, which means you've satisfied 3 children. So wherever R is standing, at whatever index it is standing, that is the number of children you were able to satisfy. And that will be your answer. Quite simple. So if I have to write down the pseudocode, can you? Probably yes. What you'll write is, okay, assume you're given a function. What are you given? You'll be given 2 arrays. Definitely one is the greed array, while the other one is the size array. Very simple. Maybe I can say n equal to greed dot size. And I can say m equal to size dot length or size dot size. Maybe you can call it some other. The name can be changed. Okay. So m as size dot size. What after this? I know there are 2 pointers. L will be at 0 and R will be at 0. There's one more thing. I need to make sure the greed is sorted. So depending on your language, you can call the internal sorting, and then you can sort the size as well. So both of them are sorted. Right? Now, you know you're testing for every cookie. So I'll be like, okay, I'll be like, while L can go on till M because I have M number of cookies, and I'll check, hey, listen, can I satisfy? Can I satisfy? What is this? The greed of R because the children are. Can this be satisfied? And it will only be satisfied if the cookie's size is greater than the greed. And if that is the case, I'll be satisfying R. I'll be satisfying R. Perfect. That's done. If it's not, doesn't matter. If it's or if it's not, I go to the next cookie. If this cookie was satisfied, fine, I'll move to the next children. Otherwise, I'll have to anyway move to the next cookie. Perfect. What I'll do is, I'll end up the while loop. And at the end of the day, what you can straight away do is, you can return, what will you return? You'll return R, yes, because that is where your answer lies. And you can complete the function. Done and dusted. What is the time complexity? Can I say that the time complexity will be run by this while loop because that is the only loop you're running? And there are 2 sorting functions. So can I say that for sorting will be n log n plus m log m plus you're running a while loop on m. So it's a big O of n. So can I say that the overall time complexity will be this one? And can I say that the overall space complexity will be big O of 1 because I'm not using any external space. But yeah, I'm definitely distorting the arrays. That is a disadvantage. But yeah, this problem will be solved in this particular way only. And this is what greedy algorithm is. You greedily try to assign the smallest values possible because that is how you can maximize the number of children who are satisfied. So yeah, this will be it for this one. So if you're still now watching and if you've understood everything, please do consider giving us a like. And if you're new to our channel, do consider subscribing to us as well. With this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye-bye. Take care.
Whenever your heart is broken.
The actual efficient size of a company is shrinking very rapidly. And so the future will...
So if you're looking out for a structured DS algo course, I must say you're on the correct channel. So in this video, I'll be telling you how to learn DS algo from A to Z in depth. Yes. So first of all, where to learn? Not on the YouTube channel because it is not structured. You'll have to head over to the website takeyouforward.org. You might be seeing it on the screen. The UI might be different some months down the line, but doesn't matter. Which course is it? There's something as A to Z DSA course. Open it up. It has 455 modules covering 18 or 19 topics. Every topic has sub-modules like sub-parts as well. So there are a bunch of problems that you will be solving in this particular course. Is it paid? No, it is absolutely free and it covers a lot more problems than what the paid courses will do. You can buy any of the paid courses and you can have a comparison done as. Before starting this video, I'd love to thank Reliable for sponsoring this third level. All the at the end, we pre-order. So if you remember, the pre-order was, that's how my traversal will look like. Be a part of my right view. Now you might think, how will this work? Very simple. Node, it's a node 7 with a level bumped up. So the level 2 comma whatever I will come across. Yes, you can have a vector and then we will call the root, the level as 0 and the vector will be passed. Root is null, return. If the size is level, add it, or go to the right and go to the left with level upgraded to +1. That's how the code will look like. Simple enough. So I hope you've understood the entire explanation as well as the code. Just in case you did, please make sure you like this video because it took a lot of efforts to make this entire tree series. Also, if you wish, you can definitely drop in a comment that will keep motivating me to make such further series. Also, if you're new to this channel, please do consider subscribing because I'm going to bring in such more series in the upcoming future as well. With this, let's wrap up this video. Let's meet in the next lecture. Bye-bye. Take care.
Whenever your heart is broken, don't ever forget you're golden.
So before starting the video, I would love to thank Reliable for sponsoring this entire tree series. So if you're tired of waiting for companies to respond to your application,